So one of the biggest reasons why people in business and marketing and management and so forth use calculus is to optimize certain performance qualities. Things like finding the maximum amount of profit in a situation, or finding the minimum amount of some negative thing like cost in some situation, right? That calculus, the derivative in particular, gives us the tools to do that. And anytime we're trying to find the maximum of some quantity or the minimum of some quantity, we call it an optimization problem. And so what we're going to do today is sort of step through the process of how to use derivatives. Not just the first derivative, which is the derivative we talked about now, but also the derivative of the derivative, which is called the second derivative, to determine local minimum, local maximum points for a function, which is the process of optimization. The first thing to know is just to recall what we talked about last week, which is what is the meaning of the derivative? Where does the derivative come from? And this sort of table, which is my favorite thing ever to prescribe to calculus students, right? Which tells us how certain properties of a function are related to properties of its derivative. So because the derivative of a function tells me the slope of one of its tangent lines, the derivative is going to be a positive quantity anytime my function is increasing from left to right on a graph. And the derivative is going to be a negative quantity anytime my function is decreasing from left to right on a graph. And at those places where the derivative is neither positive nor negative, those will be the places at which my function is neither increasing nor decreasing. And so as you might expect, if we're trying to optimize, find the top of the mountain or the bottom of a valley on a graph, those tops and bottoms are going to occur at places where my function is neither increasing nor decreasing, but just for that instant in time, remaining constant, quote unquote. Mathematicians might say infinitesimally constant. If we zoom in on that top of the mountain, if we zoom in far enough, it's going to look like it's just a horizontal line. And so its slope will be 0 at that point. And so that's the beginnings of how the first derivative is going to help us to determine where we might find the top of the hill or the bottom of a valley on the graph of a function to find a minimum or a maximum value. Probably those are places where the derivative is neither a positive number nor a negative number. So probably those are places where the derivative is equal to 0. But before we're done today, what we're also going to be able to do is take all of these observations about f and its derivative and also sort of copy them over into observations about the derivative of the derivative. And so we'll be able to talk about what it means about the graph of my function f. If f is not increasing, but if f's derivative is increasing, or f's derivative is decreasing. So we're just taking this whole table and just sort of copying it over one column to tell me something about the derivative of the derivative, f prime prime. And so the big question here is, how are the properties of that derivative of the derivative, or the second derivative, how are those properties reflected in the properties of the original graph? So what is that second derivative sort of actually telling me? I want to be able to fill in that piece of the table. By the way, I'll tell you that we can't really fill in this piece of the table with anything interesting. But we will be able to say, before we're done today, how does the derivative of f tell me something interesting, actionable about the shape of the graph of the original function f itself? So we'll have one way of optimizing, doing optimization using just the first derivative, and we'll have another way of optimizing that also uses the second derivative as part of the process as well. So we'll start with the graph of this function. So I sort of pulled this function out of a hat. It's not an unrealistic shape for a graph of a profit function to have. So on the horizontal axis, I have the amount of my product that I'm producing every month, thousands of units. And on the vertical axis, I have how many millions of dollars of profit am I making off the sales of this product. And so the first thing I'm asking us to do here is just to kind of get our bearings. So if we look at this graph, what interval of x values would you say that our company is actually making a profit on this product? And you just have to make some guesstimates because we can't really see exact numbers on this x-axis. But if you could write an inequality that describes what range of x values we're actually turning a profit, then what would you say? We can tell where a function on a graph is positive, right, just by looking for where its graph has risen above the x-axis. And so in this example, it's probably somewhere, between x equals 6 in thousands, so right about over here on the left hand, all the way up to about, let's say, 21, right? We're just sort of taking some round guesses on this. That inequality tells me where my product is profitable, because it's where my profit function has a positive value. It's above the x-axis, right? So what's happening in other places? Like, let's say over here when x is equal to 4, what would we say that's representing? So the other places on this graph where my graph is below the x-axis, that means that the y value, which is my profit value, my y value is negative. And so I would have a negative profit, which is, in other words, a loss. Usually the thing we try to avoid in business if we can, right? Right, so looking at a graph, we can tell sort of based on where we're above the x-axis, where we're below the x-axis, what the sign, S-I-G-N, of our quantity is, whether it's positive or negative. Okay, so now that we've said something about where our original function, the profit function, is positive versus negative, I want us to begin our journey towards thinking about the shape of graphs and derivatives and things like that, right? Where we want to start answering that same kind of question about positive and negative, but we want to answer that question about the derivative rather than the original function itself. So my question is, how would you compute the derivative of this function? What's a formula for the derivative of this p of x? That's going to give us the marginal profit function. So my original profit function was this third degree polynomial minus 0.1x to the third plus 2.7x squared minus 13.5x. That's the graph that we see over here on the left. And the marginal profit, which is how much profit or loss do I make by selling just one more unit of my product at any given production value, that derivative has this formula, minus 0.3x squared plus 5.4x minus 13.5. Okay, so remember what that derivative tells us, right? That derivative is telling me the slope of a line drawn tangent to this curve. So now I want us to think about the same kind of questions that we started with, which is the sort of where is it positive, where is it negative kind of thinking. And you can drag this point around the graph if it helps. Try to find an interval, an example of an interval of x values, on which the marginal profit is positive. The amount of profit that I would make by selling just one more unit is a positive quantity. I would make money on selling the next unit. See if you can come up with an interval of x values where that's true. So if we're looking for the places where the marginal profit is positive, we're looking for places where selling one more unit will actually make us a positive amount of more profit, right? The next unit we sell is going to make us money. And so that's going to happen anywhere that the slope of my tangent line, which is the marginal profit, anywhere where that slope is positive, right? So let's say that we're currently producing 10,000 units, right? 10,000 monthly units. Then that means that we're making $35 million in profit because that's the XY coordinates of this point on the profit graph. Meanwhile, the slope of the graph at that point, the marginal profit, is 10.5, which means that the next unit of my product that I produce is going to make me $10.5 million per 1,000 units produced, or if I cancel those units, $10,500 or $10,500. The next unit that I sell is going to make me $10,500 more of profit if I'm currently producing 10,000 units a month. If I'm producing 14,000 units a month, my next unit that I sell is going to make me $3,300 more, right? So the next unit is still profitable. So you might say that we're still sort of underproducing. As long as this marginal profit is positive, we can produce more and thereby increase our profit because the next unit that we produce is going to make us, it's going to net us a positive amount of profit when we sell it. That continues until we get up here. If I'm currently making 15,000 units, then according to the slope of this line, the next unit that I produce is not going to make me any profit because I'm now reaching the point where my costs are starting to overwhelm. There's not enough demand, I guess we would say, to be able to sell enough of my units at the price that it would take to cover the cost that's necessary of producing that many of my product, whatever my product happens to be here, right? And so past that point, we're now starting to overproduce. Let's say I'm producing 17,000 monthly units. If I produce one more unit, that one more unit is not going to make me a profit. It's going to lose. I'm going to lose $8,400 of profit on that next unit that I make. So if I want to increase my profits, I don't want to increase production at this point. I want to decrease production. For every one less unit that I produce, I will actually make $8,400 of additional profit at that point. So when we're overproducing, in order to increase profit, we need to decrease production, right? Because the slope of this tangent line is negative. And so in your answer here, you said that the place where we would say that the marginal profit is positive might be the range of x values in between this point over here, 3 million monthly production, where actually we're taking a bath, right? We're losing $18.9 million of profit if we produce 3 million units. But everywhere between there and 15,000 monthly units of production, the marginal cost is positive. Sorry, marginal profit is positive. Everywhere between x equals 3 and x equals 15. This is all reflected on the sort of the table up here, right? Because if I'm looking for where my derivative is positive, I will find the derivative being positive in places where my original function is increasing as we look at it from left to right. And indeed, that's exactly what's happening on this graph. Between x equals 3 and x equals 15, my profit graph is increasing as I go from left to right. And as a result of that, the slopes of tangent lines, the derivatives between those points, are all positive. Find me an example now on this graph of a place where the marginal profit is equal to 0. So when is p prime of x equal to 0? And if there's more than one such place, list all of them that you can find. Drag the point around. We'll look at how to do it with algebra too, but you can just do it with the graph for right now. So there's two places on this profit curve, right, where my marginal profit is equal to 0. The amount of profit that I would make for selling just one more unit of my product would be, I would neither make a profit nor a loss at those points. That would be 15, so the top of this mountain over here, and also 3, the bottom of this valley on this side, right? So x equals 3 and x equals 15. Those are the places where my marginal profit is equal to 0. By the way, that's different in principle than the places where my profit itself is equal to 0. Like x equals, 6. That was one of our points from before, right? What's actually happening at x equals 6? What do we call it when profit is equal to 0? So that would be called a break-even point, right? X equals 6, the place where my profit graph crosses the x-axis. Our revenues are equal to our costs at that point. We're making exactly as much money by selling as we are by producing, right? Or as it takes us to produce. And so it washes out. We break even. We get 0 profit. Not a profit, not a loss, right? But when marginal profit is 0, that just means that my profit function has leveled off. It is neither increasing nor decreasing at those points, right? Because its derivative is neither positive nor negative. So the first thing to know, and this might be the most important thing of the day today, is that if we're looking for maximum and minimum points, the first places we should look are the places where the derivative is equal to 0. Because those are the places where we know my graph is not going to be increasing and we know my graph is not going to be decreasing. We call those points critical points. Let me write this in here. Critical points. Sorry, get my pen working here. Critical points. A critical point is a place where the first derivative of my function is not positive, it's not negative. Usually that means it's 0, but it could also in principle mean that my derivative is undefined at a certain point. But the functions we work with are sufficiently nice that they're going to be defined everywhere we need them to be defined. And so mostly we care about where the derivative is equal to 0. And on our graph here, that's happening in two places. At x equals 3, where it looks like we're kind of at the bottom of a valley, we would call that a local minimum point of this profit function. And then again, at x equals 15, that's a local maximum atop of the mountain point for my profit function. So those are the places where I would say that the marginal profit is equal to 0. X equals 3 and x equals 15. The good news is, finding out where the derivative is equal to 0 gives us a good list of places where we could be at a minimum or we could be at a maximum. The bad news is it doesn't by itself tell us which ones are which. It doesn't say which one is a minimum, which one is a maximum. So that's what I want us to think about next. At which x value is the derivative going from negative to positive? And I've labeled kind of on the x-axis here where the derivative is positive and where the derivative is negative. So which of these x values is the one at which the derivative is going from negative to positive? And what's happening with the function itself at that point? So when the derivative goes from negative to positive, that means that my original function is going from decreasing to increasing. So it's a place where my function stops decreasing and it starts increasing. And so on a graph, what's happening? I'm reaching the bottom of a valley and starting to go up the other side. Right? So a place where my function stops decreasing and starts increasing again, we would call that point a local minimum. It's like like the bottom of a valley. It's a place where we're no longer decreasing anymore and we've now started increasing. Right? And so just by looking at the first derivative, the sign of the first derivative, we can figure out where that happens. Negative on the left of me, positive on the right of me. That means my function is decreasing to the left of me, increasing to the right of me, and therefore that's a local minimum point. Okay? And so of course my next question is, where does the opposite happen? Where is p prime going from positive to negative? And what's the function doing at that point? That's my point at x equals 15. Right? At x equals 15, my derivative is going from positive to negative. And so my function is going from increasing to then decreasing. It stops going up and it starts going down again. Right? That's what's happening at x equals 15. And so at x equals 15, we have not a local minimum, but a local maximum, the top of a hill. And again, we can tell that just from the first derivative, because on the left of me, for x's that are slightly less than 15, p prime is positive. So if I plug in 14, I get a positive value for p prime, right? And for x's a little bit bigger than 15, like let's say I plug in 16, my derivative is negative. And so p prime goes from positive to negative. That means my function goes from increasing to decreasing again. That means I have a local maximum. So that is how we use the first derivative to, first of all, tell me where the minimum and maximum points could be. That's where my derivative is equal to 0. And then by looking at the sign of the derivative on either side, I can tell the local minimum points from the local maximum points, just by telling whether or not I'm negative on the left, positive on the right, or vice versa. And that's how the first derivative can tell those two situations apart. So just to keep track algebraically with what we're doing, if the question that we're asking is to find all of the local max and min points of my profit function, p of x, then what this process so far tells me that I would have done is I would have first found the derivative, my marginal profit function. So that's why I had you compute that a little bit ago. Minus 0.3x squared plus 5.4x minus 13.5. 13.5. So find the derivative. This tells me increasing versus decreasing. And if I set it equal to 0, it will tell me where my critical points are. And so what I would do is I would set this expression equal to 0, plus 5.4x minus 13.5. And I would endeavor to solve that equation for x. And of course, that becomes kind of a tricky algebra problem, right? What I would do if I were solving this is I would multiply everything through by negative 10 to clear out my decimals. 3x squared minus 54x minus 135. And then I would divide everything through by 3. Divide that all by 3, I'll get x squared minus it's 18x plus 45. So basically I'm just dividing everything by negative 0.3 to get from there to there. And then either use the quadratic formula, or, because I set up this problem so I could make it whatever I want, I would just have to factor x minus 3, x minus 15. And then when I solve that, x minus 3 equals 0 or x minus 15 equals 0. So either x equals 3 or x equals 15. So from an algebra perspective, that's how we would have gotten to the point where we knew that when x is 3, we have a critical point, so the slope is 0. And when x equals 15, we have a critical point, so the slope is 0. To actually get to the classification step, I need to not just know what the value of the derivative is at those points, 3 and 15. I also want to know what the value of the derivative is on either side. And so if I didn't have this friendly Desmos graph to show me, here's what I would do. I would put on my number line here my two critical points, x equals 3, x equals 15. Right? And I would tell myself, what do I know about my derivative at that point? My p prime. My p prime is equal to 0 at those 2 points. After all, that's how we discovered 3 and 15 in the first place. That must mean that my function itself, my profit function, p, is neither increasing nor decreasing, so it's sort of flat, it's horizontal. Each of those could be the top of the hill, or it could be the bottom of a valley, or it could be something else. In order to tell which is which, we also need to be able to say something about the x values in between. So for the x values between 3 and 15, my function is either always increasing or always decreasing in between. So to figure out which it is, I'm just going to pick an x value. Let's pick one that's just, as convenient as we like. Let's say we pick x equals 4. I'm just going to pick one. If I then plug x equals 4 into my p prime function, p prime of 4, negative 0.3 times 4 squared plus 5.4 times 4 minus 13.5. Get out your calculator, you churn that out, you find out that the derivative at x equals 4 is about 3.3. But the point is not what is the number. The point is that number positive or is that number negative? Okay. And now that I've found out that that number is positive, I know p prime is positive on that entire interval between x equals 3 and x equals 15. And therefore p must be increasing. So I kind of like to draw this little sign chart where it kind of sort of shows me which direction that I know that my graph is going at these various x values. So everywhere in between x equals 3 and x equals 15, my graph is definitely going upwards. It's definitely increasing. And if I then play the same game for, let's say picking a an x value that's less than 3. Anytime you can pick 0, it's usually an easy one to pick, so I'm just going to pick 0. If I then compute p prime of 0, p prime of 0 is going to be 0.3 times 0 squared, 5.4 times 0, minus 13.5. Evaluate that out, I get negative 13.5, which we don't care about the number, but we do care about the sign of that number. It's negative. And because p prime is negative at x equals 0, it means it's negative on that whole chunk of the real number line. And when p prime is negative, p is decreasing. And so from that information alone, we know what's happening at x equals 3. We know that my profit function is going from decreasing on the left to then leveling off and starting to increase again on the right. And it's that combination that's what tells me that we have a local minimum at that point. I'll just abbreviate that, min. We have a local min there because we've stopped decreasing and we've started increasing. And if we did the same classification over here on the right, if we took, again, whatever x value we want, let's say 16, plug it in, we know we're going to get a negative number. I mean, we would do out the arithmetic if we didn't have the graph. And that negative value for the derivative would mean that my function itself is decreasing. And therefore, at x equals 15, my function is going from increasing on the left side to decreasing on the right side. It has stopped increasing and started decreasing. And that's what tells me that this point is a max instead of a min. So that's how we would implement the first derivative test using algebra if I didn't have a fancy graph and a Desmos tool to help me do this. The one thing that I think is inelegant about the first derivative test is that it requires us to do a lot of plugging in values, right? We had to first of all find the x values 3 and 15, and then we had to plug in 0, 4, and 16, these extra values, into the derivative. So we had to do a bunch of extra arithmetic in order to figure out which point was a minimum, which point was a maximum, right? There is a way to avoid doing that, and that's to use the second derivative. So that's what we're going to explore here to wrap things up today. The second derivative of a function is nothing more than the derivative of its derivative. So the first thing I want to ask you is just, what is the second derivative of this profit function? There's p of x, there's p prime of x. What is p prime prime? What's the formula for it? So the derivative of the derivative is just going to, again, using the power rule, be negative 0.6x, multiplying that by the 2, plus 5.4. And then my negative 13.5x will go away. So there is a formula for the derivative of the derivative, or the second derivative. So the more interesting question for me anyway, is what is that second derivative actually going to tell us about the shape of the graph of P? What is it going to tell us about the profit graph? So now I've added one more sort of little piece to this screen right here. And it is that not only can we see the slope of a tangent line marked in green, but we can also see this sort of purplish curve. And what this purplish curve does is it's sort of like a tangent line, except that it's not a line anymore. It's what I would call a tangent parabola. It's a parabola which just barely touches the graph of my original function and has exactly the same quadratic shape as the graph of my function at that point. So it's my tangent parabola, shown here in purple. And so I guess the question that I'm asking us to think about here is, what is that tangent parabola kind of actually telling me about the shape of this graph? So to do that, what I want to ask you about is find me an interval of x values on which the concavity of the graph, as reported by this little tool, is positive. So see if you can come up with an estimate for that. So the first thing we notice is, roughly speaking, on the left side of this graph is where we find positive numbers for this concavity, right? That my tangent parabola is opening upwards on the left sides of this graph, whereas on the right sides of this graph, my tangent parabolas are all opening downward. So we would say we have negative concavity, right? So that's the first thing that I notice. And there's a place right here in the magic in-between where actually my tangent parabola is not a parabola at all. It's just a straight line, right? So that looks like that's a point at which my graph isn't actually curving upwards or downwards at all. It's just sort of, for that instant in time, it looks like a straight line. Right? It neither has a upward-facing tangent parabola nor a downward-facing tangent parabola. So if I were to say what's an interval on which the concavity of this graph is positive, I might say that it's positive all the way from the beginning of my graph here at x equals 0, all the way up as far as right there, which is x equals 9. If that makes sense. So how would we say well, I guess this is just a definition. We will say that whenever the tangent parabola to a graph is opening upwards, whenever our concavity is positive, we say that the graph of the original function, the red curve, is concave up over here on the left side of the graph. One way to think of it is if it were to rain on top of this graph, the rainwater would actually sort of collect here where the graph is concave up, whereas where my graph is concave down, over here the rain would all run off of those portions of the graph. Another way to think of it is if you're driving a car along this graph from left to right, we're concave up when our wheel of our car is turned to the left, and we're concave down when the wheel of our car is now turning to the right. And that one point in the middle, in between the two, where we're neither concave up nor concave down, that's when my wheel is straight on ahead of me, right? So if I'm driving my car along a straight line, I know that my wheel is neither turned to the left nor to the right, so straight lines are neither concave up nor concave down. But in places where I'm concave up, it must mean that my wheel is turned to the left as I'm driving from left to right. And the places where I'm concave down, my wheel is turned to the right as I go from left to right on the graph. A mathematician would also call this a measure of what's called curvature, right? How much and how rapidly are we turning the wheel? Because also at these places where the concavity numbers are really large, that looks like where we're making the biggest sort of swerves in my curve to the left or to the right. So concave up and concave down are how we describe the shape of the graph in those moments. And so just to come back to the whiteboard for a minute before we get to the big finish slide on this. Rewind myself back here. Here we go. So we now actually have an answer to what does the derivative of the derivative tell me. The derivative of the derivative tells me the concavity of the graph of a function. So where the derivative of the derivative, where the second derivative is positive, get out of the way of my mouse here, where the second derivative is positive, that's where the first derivative is increasing. And that's where the original function, f, is concave up. So now we can add that to our chart. Concave up. Its tangent parabola is opening upwards. And conversely, where my second derivative is negative, that's where the first derivative is decreasing and my original function is concave down. And of course, if the second derivative is neither, then the first derivative is neither increasing nor decreasing. F would be neither concave up nor concave down. And often we call those points at which a function switches its concavity from up to down, or vice versa. That would be like this point right here at x equals 9. Right? On the left of it, all my parabolas are concave up. On the right of it, all my parabolas are concave down. So at that point, we're switching. And a point at which we switch concavity is called an inflection point. Anytime we switch from concave up to down, or vice versa. So in our example here, x equals 9 would be an inflection point because we're concave up on the left of it and we're concave down on the right of it. And so what I want to close with is to ask you this question. How can the slope and the concavity together tell me where to find a local minimum and where to find a local maximum? And to sort of nudge you into answering this question, think about how you would answer local minimum when blank and blank. So tell me something about the slope and the concavity there. And then local maximum when blank and blank. Tell me something again about the slope and the concavity in that case. So we will know that we have reached the top of a mountain. We'll know that we're at a local maximum when, first of all, the slope is 0. So I'll say f prime. The slope is 0. But also, we need to know that we're at the top of the mountain and not the bottom of a valley. And at the top of a mountain, our tangent parabola is going to open downwards. We're going to be concave down at the top of a mountain. Concave down. In other words, i.e., what do we know about our derivative of the derivative? When our graph is concave down, what is the second derivative being?
Negative.
Negative, yeah, right there. Right, exactly. Which, by the way, is one place where everybody makes this mistake at least once when taking a calculus class, is that maximum points happen where the second derivative is negative, which is like sort of just screws intuitively with us, because usually we think negative bad, right? But negative less than 0 means concave down, which is what happens at the top of a mountain. What about a local minimum? What's our slope at a local minimum? It's again 0, right? Because we need my graph to be neither increasing nor decreasing. So we need the derivative to be neither positive nor negative, right? We need the derivative to be 0 again. But now what can we say about the concavity? Concave up or concave down? Concave up. And a graph is concave up when its second derivative is
Positive.
Positive. Cool. So there is kind of our taxonomy of how to tell, using the first and second derivatives together, whether or not we are at a local minimum point or a local maximum point. So the first thing that we would do in those cases, let me get my screen that we were working on back here, right? The first thing that we did was we tried to figure out where were the points where my slope was 0. So we took the derivative, we set the derivative equal to 0, we solved for x. So that gave us the 3 and the 15, right? So we knew that those were our critical points, x equals 3 and x equals 15. To tell which one was a minimum, which one was a maximum, using only the first derivative, we had to check all these other x values, and that seems like not an elegant way to do it. So to do it with the second derivative instead, here's what we could have done. We could have taken that second derivative, the derivative of the derivative, and so that had the formula p double prime of x equals minus 0.6x plus 5.4. And all we would have had to have done is we would have had to ask, what is the concavity of my function at each of those 2 points? So instead of having to pick these other points and do something there, we can just worry about x equals 3 and x equals 15 themselves, and just evaluate the second derivative at each of those places. P double prime of 3, negative 0.6 times 3 plus 5.4. That's positive 3.6. which, by the way, is also the number that the concavity came up with here on this graph, right? Positive 3.6. And the important part is that it's positive. And because it's positive, P double prime is positive at that point. Right? That meant that P was concave up at that point, which is how we would have known that it was a minimum, even without checking the first derivative on both sides. And in the same way, if we checked x equals 15, the second derivative at x equals 15, negative 0.6 times 15 plus 5.4, that, it turns out, gives us negative 3.6. And because that's negative, then we know for sure that at that point, my original function is concave down. And because it's concave down at a critical point, that's how we know that it's a local maximum at that point. Right? So what I'm hoping is coming through in this whole activity that we just did is just that, right? That in order to find the places where we are at a local minimum or a local maximum of a function, the first thing we want to look for are the places where the slope is zero, right? The places where the first derivative is equal to zero, the critical points. So we first had to get this numbers 3 and 15, right? We took the derivative, we set it equal to 0, we solved it for x, and that's how we knew that my critical points were at 3 and 15. But the second step to that is then to classify which of my critical points is a local minimum, which one is a local maximum. We can do it by making reference to the first derivative, but that requires us to check values on either side of all of my critical points, right? And tell where the first derivative goes from negative to positive or from positive to negative to differentiate between minimum and maximum. Or we can take the second derivative of the function and evaluate that second derivative at each of those two places. And when x is equal to 15, my second derivative has a negative value. When x is equal to 3, my second derivative had a positive value. And so those values themselves can also tell me, based on whether my graph is concave up or down, whether or not we're at a local minimum or local maximum. So you should be able to have both of those tools at your disposal, either the first or the second derivative test, to find and classify all the critical points of a function. Most of the time, you get to choose which one of those two that you do, but it's good to have practice with them both. You know, every once in a while I might ask you specifically on a quiz, for example, to show me how a first derivative test would work here, show me how the second derivative test would work there. But that's the broad strokes of it. And because this has the power to optimize a function, this is why we care so much about the derivative in a business context, is it can find those tops of the hills and those bottoms of the valleys when those are important business things to know, and they frequently are.